Rational zero theorem. Rational zero theorem gives us a list of possible rational zeros of a polynomial function. Not every number in the list will be a zero of the polynomial, but every rational zero of the polynomial will appear in that list. So rational zero theorem says if we have a given polynomial, then all the possible rational zeros are in the form of p over q, where p is a factor of constant term and q is a factor of the leading term. Let's see some examples. Here's a given example. Find the list of possible rational zeros. First thing to note that the degree is 5, so that means there's total 5 zeros. There's 5 total zeros in this for this polynomial. Some might be repeating. So if it does have any rational zeros, if it does have any real zeros, they're going to be of the form of plus minus p over q, where p is a factor of the constant term and q is a factor of the leading term. Let's go ahead and list the factors of the constant term. 12, 1, 2, 3, 4, 6, 12. And q is going to be the factors of the leading term, which is just 1. So possible rational zeros in this case is going to be divide p with each of the q's, and that would be our possible. In this case, dividing with 1 makes no difference. So plus minus 1, plus minus 2, plus minus 3, plus minus 4, plus minus 6, and plus minus 12. These are all the possible rational zeros for this given polynomial. This polynomial is going to have 5 total rational zeros, and it's going to be, if it does have any real zeros, they are in this list. Some of these are not going to be the zeros. We'll have to do synthetic division or factoring and figure these out. But right now, we're only creating a list of possible rational zeros. Another example, using the rational zero theorem, figure out the possible rational zeros for this polynomial. We know the possible rational zeros are going to be of the form of plus minus p over q, where p is factors of the constant term, which in this case, constant term is 2. Only factors of 2 are 1 and 2. And q are going to be the factors of the leading term, which is 15. 1, 3, 5, 15. So let's go ahead and create our list of possible rational zeros. Plus minus 1, plus minus 2. So divide p with each of the q's, and the next would be plus minus 1, plus minus 2, plus minus 1/3, plus minus 2/3, plus minus 1/5, plus minus 2/5, plus minus 1 over 15, plus minus 2 over 15. Here we have list of 16 possible zeros, but in reality, if we use Desmos, we can check that these are the only 3 zeros that this polynomial, only 3 real zeros does this polynomial have, because this polynomial have 3 total zeros, and all 3 zeros are real zeros. We can check by using Desmos for graphing. These are going to be the real zeros, and they are in the list. So not every single item in the list will be your rational zero, but all the rational zeros do appear in the list. Descartes' rule of signs helps us narrow our list of possible rational zeros down. Descartes' rule of signs says if we have a polynomial with real coefficients, the number of positive real zeros is going to equal the sign changes of f of x, or is less than that by an even integer. The number of negative real zeros of a polynomial, it's either equal to the number of sign changes in f of negative x, or is less than that by an even integer. Let's see how Descartes' rule of sign works. How does it help us bring our list, narrow down our list of possible rational zeros? So here's f of x given to us, number of positive real zeros. So in this case, the total real zeros, we know there's going to be 3 total zeros. Some can be real, all 3 can be real, or there can be complex zeros as well. The number of positive real zeros is equal to sign changes in f of x. And if you look here, f of x, there's no sign changes, so there's no positive real zero in this case. No positive real zero. That means in my list of possible zeros, I don't need to check any of the positive numbers. They're not going to work out. They're not going to be zeros for this polynomial. Now let's think about number of negative real zeros. For that, we need to figure out f of negative x. F of negative x is going to equal negative x to the third plus 2x squared minus 5x plus 4. And how many sign changes here? 1, 2, and 3. Number of negative zeros is going to be either 3 or less than that by an even number. So either 3 or 1 negative real 0. So I will be testing my negative numbers, not the positive numbers in this case. If I have 3 real zeros, then there's 3 negative real zeros, then that's how many total zeros I have. But if I have 1 negative real zero, that means I have 2 complex zeros, because in total there's 3 zeros. And rational zero theorem only gives us a list of possible real zeros. It does not say anything about complex zeros. Trick to check if 1 or negative 1 is a zero of a polynomial. Write the polynomial in the standard form. Add zeros for any missing term. So if you have missing powers, you don't have an x squared term or you don't have a x term, add a 0 for that. If sum of alternate terms is same, then negative 1 is a 0. If sum of alternate terms is opposite, then 1 is a 0. Let's go ahead and factor the given polynomial. So factoring by grouping is not going to work here. If we group the first two terms and last two terms, we're not going to have the same thing in two parentheses. So factoring by grouping will not work. Let's come up with the list of possible zeros here. Total number of zeros is going to be 3 here, because the degree is 3. Total number of zeros is 3, because the degree is 3. So list of possible rational zeros, which is going to be plus minus factors of the constant term divided by factors of the leading term, which is 1. So we just have to list all the factors of 100 plus minus 1, plus minus 2, plus minus 4, plus minus 5, plus minus 10, plus minus 25, plus minus 50, and plus minus 100. These are all the possible factors for 100. So these are all my possible zeros. So we have 1, 2, 3, 4, 5, 6, 7, 8, 16 possible zeros in this case. Out of those 16, only 3 are going to work out. Let's quickly check if 1 or negative 1 is a 0. So if I add the coefficients, 1 minus 25 is negative 24, and 4 minus 100 is negative 96. They are not same, they're not opposite. That means 1 or negative 1 are not the zeros. Next number I'm going to go ahead and try is going to be 2. We can also think about how many positive zeros and how many negative zeros. So how many sign changes? The number of positive zeros in this case is going to be the number of sign changes in f of x. So 1 sign change, so number of positive zeros will be only 1. Number of negative zeros is going to be, there's only 1 positive 0, and let's think about f of negative x. That's going to be, f of negative x would be negative x to the third plus 4x squared plus 25x. There's going to be, let's see, we'll have to write it down. So let me erase this. Figure out. Okay. F of negative x will be negative x to the third plus 4x squared plus 25x minus 100. Right? So how many sign changes do we have here? 1 and 2. So there's going to be 2 negative zeros, 1 positive 0. There could be 2 or 0 negative zeros in this case. Right, so let's go ahead and try 2 here for synthetic division. 1, 4, negative 25, negative 100. Keep in mind to add a 0 for the missing powers. In this case, I have none. So that turns out to be 12, which is negative 13, negative 26, negative 126. 2 is not a 0. Next number I'm going to try here is negative 4. So to try negative 4, we will be doing synthetic division with negative 4. 1, 4, negative 25, negative 100. Negative 4, 0, that turns out to be 0. Negative 25 adds up to 100. So we can see negative 4 is a 0. If negative 4 is a 0, then 4 is a factor. The benefit now is I am down to a lower degree polynomial. I had a cubic polynomial, but next, because I found 1 0, I can say that this polynomial, I'm down to a quadratic polynomial now, which is going to be x to the second power minus plus 0x minus 25 equal to 0. So I do have a lower degree polynomial now, which is x squared minus 25 is 0, and that's factorable. X plus 5, x minus 5 is 0. So my zeros turn out to be, in this case, x equals negative 4, 5, and negative 5. These are my 3 real zeros in this case. So if I were asked to factor the polynomial, like in this case, I was being told to factor the polynomial. So the factors are going to be x. If negative 4 is a 0, x plus 4 is a factor. Negative 5 is a 0, x plus 5 is a factor. X equals 5 is a 0, x minus 5 is a factor. Right, so here's the factors of my polynomial. See another example. Solve this equation, x to the fourth minus 5x to the third plus 20x minus 16. To solve this polynomial, I'm going to come up with the list of possible zeros, which is going to be, there's 4 total zeros. Not all of them are going to be real. They might be, they might not be. So let's check. List of possible rational zeros will be factors of 16 because my leading term is 1 in this case. So plus minus 1, plus minus 2, plus minus 4, plus minus 8, plus minus 16. Let's quickly check if 1 or negative 1 are the zeros. So if I add the opposite alternate terms, I don't have the x squared term. X squared term is missing here. So let me go ahead and add the x squared term here as well. Check if 1 or negative 1 is a 0. To check that, I'm going to write it in the standard form. So sum of the alternate terms, 1, 0, negative 16. 1 plus 0 minus 16 gives me a negative 15. Negative 5 plus 20 gives me a positive 15. So notice if we get opposite, if alternate terms add up to opposite numbers, then 1 is going to be a 0. So that's easy. I can see 1 is a 0 in this case. So let's go ahead and do synthetic division with 1. Then I would be down to a third degree polynomial. When we do synthetic division, do not forget to include zeros for the missing powers. 0, 20, negative 16. 1, negative 4, which is negative 4 here. And that's negative 4 again. Negative 4 is 16, 16, 0. Now I have a cubic polynomial in this case. So my next polynomial, I'm down to a third degree polynomial. Let's go ahead and see now. Next, this is going to be x to the third minus 4x minus 4x. X to the third minus 4x squared minus 4x plus 16 equal to 0. So that's my new polynomial. And I can quickly check that 1 and -1 are not going to be zeros now. So I don't need to try them again. But it looks like this polynomial is factorable. I can factor by grouping. If I pull out x squared, I would have x minus 4 inside. Pull out -4, x minus 4 inside. So x squared minus 4, x minus 4 is 0. X plus 2, x minus 2, x minus 4 is 0. So from here, I have my other 3 zeros because I could do factoring by grouping here. So all the zeros for this polynomial are x equals 1, 2, -2, and 4. 1, 2, -2, and 4 are the zeros for this polynomial. So those are the x-intercepts, those are the roots. If we were to graph it, these will be my x-intercepts. All right, see another properties of polynomial equations. If a polynomial equation is of degree n, then it has n roots. Some might be repeating. If a plus bi is a root of the polynomial equation, then a minus bi is also a root. Complex roots occur in conjugate pairs. So if 2 plus 3i is a root, then 2 minus 3i will also be a root of the equation. Complex roots occur in the conjugate pair form. All right, so zeros of a polynomial, we can have real zeros and we can have complex zeros, and real zeros can be found by using rational zeros. Complex zeros can only be found when you're down to a quadratic. We'd have to we would have to figure out using quadratic formula. We'll have to figure those out. See, here's a strategy for finding zeros of a polynomial. Let's see some examples. Solve 3x to the third minus 8x squared plus 5x minus 2. So here, let's come up with the list of possible rational zeros. Possible zeros. One thing I can see that there's 3 total zeros because my polynomial is of degree 3. Some zeros can be repeating. So if we do synthetic division with one number, that number could be again a 0. So we can redo synthetic division with the same number. Possible zeros will be plus minus 1, plus minus 2, plus minus 1/3, plus minus 2/3, where P is factor of the constant term, Q is a factor of the leading term. So let's say 1 or -1 are the zeros. We can 3 plus 5 is 8, and -8 minus 2 is -10. So 1 and -1 are not the zeros in this case. So I don't need to try. 1 or -1 are not the zeros. Those are usually the simplest ones. Those are the ones I start by trying. Let's go ahead and try 2 first. That's the next number on the list. Don't forget, if there's any missing powers, add zeros for the missing powers. So 3 comes down, 3 times 2 is 6, -2, -4, 5 minus 4 is +1. 1 times 2 is 2, and we will have 0 as a remainder. That means 2 is a 0 for this polynomial. If 2 is a 0, I'm down to a quadratic equation, which will be 3x squared minus 2x plus 1 equal to 0. We can solve it using quadratic formula. 2 plus minus square root of b squared minus 4ac divided by 2 times a. Quadratic formula is -b plus minus square root of b squared minus 4ac over 2a. That would leave us with 4 minus 12 is -8 over 6. And we can pull out an I plus 2 plus minus I 2i root 2 over 6. And we can factor out a 2 from the numerator, cancel with the denominator. We'd be left with 1 plus minus I root 2 over 3. So all the zeros for this polynomial, solutions for this polynomial, or roots or zeros, are going to be x equals 2 and 1 plus I root 2 over 3, 1 minus I root 2 over 3. There were 3 total zeros, and there's 1 real 0 and 2 complex zeros. Complex zeros always occur in pairs, so you can have 2 or 4 or 6 complex zeros for any given polynomial. See another example. I'm going to solve this polynomial equation. It's a 4th degree, and factoring by grouping is not going to help because I will not have the same numbers in the parentheses. Let's think about possible rational zeros. So make a list of possible rational zeros. Possible rational zeros. Okay, so there's total 4 zeros. Total 4 zeros. And how many positive and how many negative? Let's think about Descartes' rule of sign as well. That helps us narrow our list down. So going from positive to negative here, sign changes, negative to positive here. So positive zeros, either 2 or none. And f of negative x will be x to the 4th minus 6x squared plus 8x plus 24. So 1 negative real 0. 1 negative, either 2 or none positive. All right, so let's go back to our list of possible rational zeros, which are the factors of constant term divided by factors of the leading term, which in this case is 1. So plus minus 1, plus minus 2, plus minus 3, plus minus 4, plus minus 6, plus minus 8, plus minus 12, plus minus 24. These are all the possible factors of 24. 1, 2, 3, 4, 6, 8, 12, 24. Yep, we didn't miss any. Let's quickly check if 1 or negative 1 is a 0 here. That should help us. 1 or negative 1. So the opposite term or the alternate terms, 1 minus 8 is negative 7. Negative 6 plus 24 is going to be 18. No, they're not same. They're not opposite. So that means 1 or negative 1 are not zeros. 1 or negative 1 are not zeros. So the next number I'm going to try in my list is a 2. Let's go ahead and do synthetic division. I don't have x to the 3rd term, so I will have to add a 0 for the cubic term. Minus 6, minus 8, and 24. 0 plus 2 is 2. 2 times 2 is 4. Negative 2, that's a negative 4. Negative 12, and that's negative 24. And we have the remainder 0. So x equals 2 is a 0. Now the nice thing is we had a 4th degree polynomial. Now we're going to be down to a cubic polynomial. So let's see, cubic polynomial is going to be x to the 3rd plus 2x squared minus 2x minus 12 equal to 0. X to the 3rd plus 2x squared minus 2x minus 12 equal to 0. Again, I can see 1 and negative 1 are not the zeros. And my list, if I go back and look at my list, I can eliminate 24 from the list now because that's not, for the new polynomial, 24 is not a factor because my constant term is 12. But any of the other ones can still be the zeros. So I'm going to try positive 2 again. There's no fixed way of telling which ones are going to be zeros. It's just check by doing synthetic divisions, or you can use the hints, like, because I said there were 2 positive zeros, so I'm going to try positive 2 again. Could be 2 or 0 positive zeros. So 1 times 2 is 2, 2 plus 2 is 4, 4 times 2 is 8, 6 times 2 is 12, and the remainder is 0. X minus 2 is a factor, or 2 is a 0 again. 2 is a repeated 0. 2 is a 0 twice here in this case. So now I'm down to a 2nd degree polynomial, x squared plus 4x plus 6 equal to 0. We can go ahead and use quadratic formula. b squared minus 4ac divided by 2 turns out to be negative 4 plus minus square root of negative 8. 16 minus 24, that would be negative 8 over 2, which is negative 4 plus minus 2i. We can pull out a 2i root 2 over 2. If we simplify, factor a 2 out from the numerator and cancel it out with the denominator, this is what we are left with. So for this polynomial, we have 4 zeros, which is 2, 2, and negative 2 plus minus I root 2. All right, so if we were to factor this polynomial, we can go ahead and write it as x minus 2, x minus 2, x minus negative 2 plus root 2i, and x plus minus negative 2 minus I root 2. Well, that's not legible, so I'm going to add the extra factor here, x minus negative 2 minus root 2i. These will be the factors of this quadratic equation, a fourth degree equation. All right, that was all for this video. We talked about rational zero theorem, and we talked about finding the real and complex zeros of a polynomial.